what should I do? I've given all this. So don't worry about the course right now, but I would just say, if you want to be an expert in computation or data science, then what you need to, well, computation. Data science, I'm not an expert, but I'll take about computational science. So as a user, learn Linux. Though we are going to use only Python for this course, and that part is Python works on all three systems, Windows, Mac, and Linux. So you really don't need Linux per se for this course, but if you want to really master computing, then you need to learn Linux. Algorithmic thinking, that's what, if you're not knowing programming, I will contrast. I will say that, okay, this is called algorithmic thinking. So this is slightly different than what we do in math, standard physics math, mathematical physics. So mathematical physics involves integration, linear algebra, complex analysis. Here, the things will be working with integers. So how to sort an array, given a set of numbers, how to put them in ascending order. So that is not going to be helped by complex analysis, what you learned. So it requires a different kind of thinking, how to work with arrays, how to vectorize, how to make it fast, how to make your code fast. That requires a different kind of thinking. It is not the same as what we learn in mathematical physics. So programming languages, that many of them, but in physics or in engineering, normally we use first three, C, C++, Fortran. Java is not used often. For interface, way we interface, Java is used, but I think we can focus on the first three. Now this is called interpreted language. These are the four interpreted language which are used heavily. So what's the difference? So compiler languages, you put in the whole code. So you write the full program. Like for example, I want to solve a differential equation. Then I write the full program. I basically create an array, and for each variable, then I time step it. So you need to start from the beginning and write the whole code, and you give it to a software called compiler. And compiler converts this English-looking like language, like in C language, which is higher level language, and converts it to object code, like which is zeros and ones. And computer only understands zeros and ones. It doesn't understand for loop, if loop. It just understands zeros and ones, and it does execute. So this package which converts this C language code to zeros and ones called object code is called compiler. But you need to give the full code to the compiler. You can't give half the code and say, well, let's see what the result of this half the code is. However, okay, so that's compiler language. In interpreted language, you can do step by step. You can declare an array and you put a enter. So you'll see that Python, you can basically build the code line by line, if you like, or you can build a code function by function. So this is called interpreted language. So we are basically talking to the computer, and computer is responding live, like language translator, So this interpreter. So I speak only English, but I want to communicate to somebody who knows French. So the interpreter will convert English to French, but it will do live. That's what the computer does. It does live translation of the Python code to object code. Okay, so machine and the language. So these are the two different beings, and it's translating line by line. So interpreted language are easy to learn because you don't need to worry about full code, easy to compile, easy to run basically, and also easy to learn. So that's why Python has become very powerful. Very popular, not very popular among at least the first learners. Python is a standard language now. So this is a website where you can see the comparison. Now, so what should I do as a computational scientist, as a programmer for science and engineering? I suggest that one should learn one compiler language at least and one interpreter language. Okay. It turns out Python is slow compared to compiler languages. So if you want to write large code, then you have to go to the compiler languages. Though right now there is a lot of emphasis on making Python fast as well. Okay, so there's a possibility that Python itself may become. I mean, you can write large codes in Python, and you can run it. I mean, it can be fast. One thing for Python, one important, one advantage of Python is that all the machine learning tools are at present developed in Python. Okay, so that's one reason why it has become a very important language. So Google, all that like TensorFlow is in Python. Okay, so if you want to learn machine learning, then Python is a language. So that's why Python has become very, very important at present. Now there's one called something called Wolfram Alpha. You can so this by Wolfram, who wrote Mathematica. So Wolfram Alpha is free. It's a web interface. You can do quite a few things on Wolfram Alpha platform. It's supposed to be natural language processing. So I can say integral of x squared. So it'll give you x cubed by 3. So it can do quite a few things on the fly. So for this course, we'll use Python because it's simple and we can do lots of things with Python. Of course, it's a PG level course, so I expect that everybody knows some programming. So it's not that I'm starting from scratch, but maybe some people are starting from scratch. I don't know. So I'll take a vote after this presentation, okay? And moreover, this course will be focused more on numerical computing, means algorithms. So we want to spend less time on language. We simply cover language and simply go to quickly go to the numerical aspect. So about the course, so there will be two parts. One is on language. So I will kind of quickly go through them for you because this is a PG level course. But I will cover these aspects like hardware, software, how to be a good programmer, algorithmic thinking, Python. So I can also say that many physics students, okay, I mean, among you, there are some very good programmers. I didn't mean to, my comment is not for them, but many physics students write a very, very bad programs. Okay, so I've seen one program I was many years back. So the student had variable name I1, I2, I3, I4, I5, I6. I mean, that code was very rubbish. So I think we should learn how to write good programs. We can't simply write variables like I1, I2, I3, I4. That's not good. Okay. So I think I will emphasize how you should write the code. Now, second part will be numerical analysis. It has many algorithms. So we start with, this is how I will cover it in this course. Some people put linear algebra before, but I'll start with interpolation. So there was a statement that interpolation is the mother of all numerical algorithms. In fact, it's true. I will show you that interpolation is a starting point for many algorithms. So though it looks very trivial, I mean, linear interpolation, you put a point between 2 points, but it's very clever algorithms are there in interpolation, and it builds algorithms for differentiation, integration, ODE solvers. So these are thing I'll follow. So I'll also say that when I did numerical methods in my undergrad, I simply did not like the course because there was no pattern. Rangakutta method, Euler method, so they all look disjoint. But no, I mean, there is a pattern, and that is what now I like it because I understand the pattern. And the pattern is there is certain beautiful mathematical aspects in these algorithms. By the way, you'll come across all the big names like Lagrange, Gauss, Hermite. Gauss will come many times. Newton also will come, and they are same Newton. Okay, it's not some other Newton, Isaac Newton. So Gauss integration procedure is beautiful. I mean, that's you will be amazed how we can do a fast integral. In fact, accurate integral. Accurate means really accurate. With zero error by Gauss method. not for all functions, but for functions, he also tells you for which functions the integration can be exact. Like Hermite's polynomial, no? When we can do exact integral with the numerical methods by Gauss method. So now I see the pattern and I'll try to communicate the pattern to you. And you see there is certain underlying mathematics which you should I'll try to communicate. It's up to you whether you like it or not, but I will try to do it. So we have enough time. We'll do Monte Carlo in this course. I didn't do it in 473, but I will do it here. Now, so I said programming is an art. I mean, so I will emphasize on few things, but some of it you have to do it yourself. I mean, this you have to program, not me. I'm just going to give you tips. So practice. You really need to practice. It is like swimming. So you can't learn swimming by theorizing. So you need to practice. And write good programs. It should be good choice of variables, indent the code. By the Python, if you don't indent, it won't run. So that's something the designer of Python thought about it, that it has to be indented and it should have good programming structure. Now, so I mean, I like to write good programs. So I kind of, if I'm not happy, then I rewrite it. So we should really write good programs. Now, references, I will give my notes, which are, I think, which has grown over time, which has become good notes. This book is, there are two more books which I recommend. The Computational Physics with Python by Newman and Fuzzy. So there are many books. Okay, I may refer to some of them, but I will basically use these two references. My notes is basically built out of Fuzzier's ideas. This book is not so easy to read, but I try to simplify it. I mean, I think this book is excellent. Fuzzier is an excellent book.